Okay, so hi, welcome to this podcast. We have a very special guest. We have a researcher, Wolfgang Ketterle, Professor Wolfgang Ketterle. Wolfgang Ketterle is a researcher at MIT who does research in the field of experimental physics on ultra-cold atoms. He has won several awards for his research, more particularly, of course, the Nobel Prize in 2001 for the realization of the Bose-Einstein Condensate, which will be one of the topics of today. So hi, welcome. How are you?
Hello, I'm fine.
Okay, good. So actually, before to talk about your research, I would like to talk about your labor as a professor, the work you do as a teacher. I have never taken an official course with you, but I have seen some of your lectures that are available on YouTube with MIT. So I guess the first, you have a very passionate and very clear way of explaining you make complicated topics look simple, which I think is what a good professor does, or what at least he attempts. So I guess the question is, what role does teaching play in your life, and how does this complement your work as a researcher?
For me, it's important to combine teaching with research. So when I teach, I draw from research. I'm not teaching a dead subject. I'm teaching a subject which is alive through research, and I try to prepare students for understanding the material in such a way that it enables them to do research. But then there's also the other component. I think by permanently teaching, it keeps me thinking about the concepts and keeps me very familiar with the basic concept. And I think in the end, this also enables me to do better research. So I think research helps the teaching and teaching helps the research. It's important to do it together.
Okay, I see. For example, maybe a good example of how good, or what I like about the way you explain things is there was one time where a friend sent me a video, and it's where you're explaining there's this problem with the kilogram, that it was not, apparently there was some controversy around the way it was defined. And to be honest, like at first, the thing, like there's so much fun stuff and exciting stuff in the internet. So if one person sends you a video, an hour-long video about the kilogram, you're like, should I watch this or not? But I watch it, and you make it seem like the most fascinating subject. And I don't know, it's very cool that something like the kilogram, that maybe on the first sight, maybe it doesn't seem like the most exciting topic. You really highlight the importance of this subject. So I guess I would like to ask you about that. First of all, what was the problem with the kilogram? Why is this important? Why people should care?
So actually, yeah, let's go back to the new definition of the kilogram. I don't think there was a real controversy. It was just a question, how do you explain something to the public? And the kilogram, as you know, is now no longer defined by this artifact, this metal cylinder in Paris, which is exactly 1 kilogram. It is defined by giving Planck's constant a defined value. And now there was a challenge. How do you explain to the public, how do you explain to a high school student what is now 1 kilogram? And people from Metrology Institute who were working on the new definition of the kilogram, they started explaining it, H has the unit of action. Action is kilogram meter per second. And if you combine it with a speed of light, you get kilogram out of it. But is that an explanation? It reiterated the definition, but at the end of the day, a student could not go and say, I can now explain it to my parents what the kilogram is. And so I felt there must be a simpler way to explain it. And with my knowledge in atomic physics, I just coined the definition that if you have, a cavity and fill it with photons, if you have a defined number of photons, this is exactly a kilogram. I mean, it's the same if you define charge. If you take so and so many electrons, that's 1 coulomb. Or if you, let me try to give, so that there is a very clear understanding. If you want to define charge, you say there is something which is an elementary charge, and so many units of the elementary charge is a coulomb. And similarly, with a kilogram, there is 1 standard particle, and if you have so many standard particles, they weigh 1 kilogram. It's just that the way how the definition is now structured, this fundamental particle, which has a specified mass, is now the photon. The photon emitted at the frequency of a cesium clock. This is how the definition works. Okay. And this was, I think it's conceptually easy. I mean, I could just draw a cartoon picture. Here is a box full of those photons, and this box has now an extra kilogram because so many photons are inside. Of course, it's just a thought experiment. You could never generate this box. You could never make it. But when people said, that doesn't make sense, also I said, it makes sense conceptually. And you have to really separate when you explain something, what is the definition, what is the concept, and what is the technical realization. So, I eventually, I wasn't really involved in the definition of the kilogram, but I have, friends and colleagues in the Metrology Institute, and I went to them and said, you have to do a better job explaining the kilogram to the public. And then they kind of said, well, can you write up something? So then I started writing up an article and giving popular talks on the subject.
Okay, yeah, but for people who is watching, I really recommend to watch on YouTube the hour-long talk. It's really exciting, and it's really, you explain it much more detailedly, and it's really exciting.
But my website has also a reference to the Physics Today article, which is a popular article. And also when the new kilogram was defined, I had a short 2-page summary how high school teachers could explain the kilogram to their class.
Okay, so you really check it. It's really good. And something that caught my attention is that in a way you use photons to define the kilogram. But I mean, normally I think, at least I and many people, I think we always, the way that something I find very exciting is that you use the kilogram in a way, it's also an excuse to talk about physics, about different subjects. And for example, you also talk about light. And normally when we think about light, maybe we don't think about something to define the kilogram, because we always, or at least in the past, we have been taught that light has no mass. But I think it's more complex than that, really. Or I don't know, what's your perspective?
Well, it's a little bit richer, but I don't think it's really very complicated, because according to Einstein, E, energy, equals mc square. So if you add energy to a system, you've added mass to the system. So when you take, a cavity, just imagine it's a box which has perfectly reflecting mirrors, and you put in light. Of course, we don't have such perfect mirrors, but just assume the light is in the box for very, very long time. You can now take this box, put it on a scale, and you find that the box is now heavier because there are photons, there is energy inside. So in that sense, it is a real mass. It is an gravitational mass, it is an inertial mass. A box filled with photons has a real mass. The only thing about light which does not have a mass is a single photon, because a single photon just moves at the speed of light. And now I'm saying it a little bit loosely, you cannot put it on a scale and measure its mass. Okay. And of course, also, it has a rest mass, which is 0.
Okay, I see. And I don't know if I remember correctly, but I think this idea of having sort of or fundamental or the kilogram, or the things that we use to measure things, so to say it, I think for scientists, even going back to Planck, it was very important to define the way we measure things in terms of the fundamental constants of nature, right? It seems like for some scientists it was really important for this.
Well, it really depends. People have, metrology is really the science of doing measurements, and of course initially the system of metrology was also done to support commerce. You want a clear definition of a kilogram, because if you trade goods and if you sell a kilogram of something, you wanted to make sure there was a reliable way of knowing that this is really a kilogram. So what happened is that you have really gone from natural objects to man-made objects to fundamental constants. For instance, originally a kilogram was defined as the mass of a liter of water. But this is not easy to do because pure water has also some gases dissolved. It's very difficult to realize that. Of course, if you say the kilogram is a liter of water, everybody can have a defined kilogram because water is everywhere. But then people realize that at the level of whatever tens of microgram, different liters of water are not the same because you cannot prepare them in that way. So then people went and defined the kilogram by this one cylinder which was kept in Paris. And this was eventually more practical and more accurate. Now, in the 21st century, we can replace the kilogram by Planck's constant. And with the knowledge of Planck's constant and atomic clocks and all those things, we can now create kilograms which are as accurate as the kilogram which was kept in Paris. But 20 years ago, people would not have been able, the definition, define h bar, use a new definition of the kilogram in terms of fundamental constant, could have been done. But this would have only defined a microscopic mass. But in commerce and for measurement, you need a macroscopic mass. And this bridging the gap between the mass of an atom and the mass of an object, this required technology which did not exist. So we did not have the option to define or if we had defined the kilogram through a fundamental constant 20 years ago, it would have been worse for metrology.
Okay, I see. Okay, and for example, I mean, because you have lived in the US for a very long time, and in the US, of course, they still have this system of feet, inches. They don't have the international metric system. In a way, I understand that in science, of course, it's much more convenient to use the metric system. But in an everyday life, what I'm trying to say is that I do understand to some degree why maybe people in the US don't see the point of changing to the international metric system because you're used to. And maybe, for example, if you ask me now to tell me what is 80 Fahrenheit, and maybe the thing like normally you develop an intuition of the units that you measure in terms of what you're used to. So to ask a whole society or a whole country to change units from one day to another, is this something? I understand that sometimes there can be a certain resistance, but I don't know if you have any type of opinion about this, or you're just...
My opinion is that we live in an international world and we should all use the same units. And I think the US should have switched to metric units. It was more sort of I would call it laziness. It's an effort to switch.
Okay.
But people now have metric units in Canada, so people were able to switch, and you can measure. It really just takes a little bit of an adjustment to start measuring temperature in Celsius and not in Fahrenheit, or if you go on a car to measure, the speed in kilometers per hour and not miles per hour. I think it's just a transition.
Okay, so.
But also, I mean, in the scientific world, everything, of course, in the US is SI units.
Yeah.
It's more in common life that people want to use, gallons and inches and feet and miles. I sometimes feel it's actually a little bit stupid. It's, people should learn about it and should learn about new units and a lot about, there's also an ignorance. If you ask, an American person, how many inches is a mile? It's really difficult, how many inches is a mile, because it's not just factors of 10, you take, what's the conversion between inches and mile? 12 inches is a foot, 3 foot is a yard, and I think 1760 yards is a mile. So I have to think about it, but you see, it's complicated. And so if you have units where most people on the street cannot even tell you, how many inches is a mile, because they cannot connect the two things because it's too complicated, this shows me it's not really, it's really an obsolete way of measurements.
Maybe I was being a bit condescending, but yes, I guess really if there is no reason to hold on to this a bit archaic system, then I guess one should try or make an effort to modernize them. Yeah.
I mean, okay, some people would say there is something natural to use, a foot, because a foot is, the length of your foot, and a foot is more natural than a meter. I mean, okay, come on,
Okay, yes.
It is clear that an inch was sort of a finger and a foot is a foot, so you had a little bit more the human scale in the units, but I think it should be so straightforward to use centimeters and meters in daily life.
Okay, that's okay. I had to ask, but it's nice to know your opinion. And yes, I think you're right. Of course, I have to bring the Bose-Einstein Condensate. It's something that I have to do. So first of all, if you could explain what is a Bose-Einstein Condensate?
Yeah, I often explain a Bose-Einstein condensate with the analogy of light. So, everybody knows by now that there is a big difference between light coming from a light bulb and a laser beam. And you can describe the difference that a light bulb emits light in all directions. The photons are in different modes. It's incoherent light. Whereas light out of a laser beam is monochromatic, and you can say all the photons march in lockstep in the laser. They propagate in the same way. And now the same distinction applies to a Bose-Einstein condensate now in the material world. In a thermal gas, atoms move randomly in all directions. They are incoherent, whereas when you have a Bose-Einstein condensate, all the atoms march in lockstep. They are in one mode, they are in one quantum state. So if you want, which is not always easy, to explain a scientific discovery in one sentence, I would say it in the following way. The Bose-Einstein condensate is for atoms, what the laser is for light. Okay. Or Bose-Einstein condensation means that we have matter, atomic matter, with the properties of laser light.
Okay, I see. And yes, and I think this theory of the Bose-Einstein condensate, obviously because of the names, it goes to this, the Indian physicist Bose and Einstein. And to be honest, I'm not quite familiar of maybe the history of the theoretical conception of this. I don't know, do you know more about how theoretically it was formulated, or maybe you could...
Yeah, sure, I know the original literature. So the story is the following, that we have to go back to 1920 or so. Mm-hmm. This were in the early days of quantum mechanics, when people had not developed yet the understanding of quantum mechanics a la Heisenberg and Schrödinger, but they had a Bohr model, they had Planck's explanation for the black body spectrum, and they had the idea of photons by Einstein. So this was the early quantum mechanics, where people started to see elements of the quantum theory emerge. And what happened is that the Planck spectrum for black body radiation was well known from, close at the turn of the century, I think, when did Planck discover the black body spectrum? 1898 or something. So it was really at the turn of the century. But then Bose gave a rederivation. He derived the Planck spectrum in a new way. And it was done in a way where he looked at photons and calculated the number of possible quantum states in a statistical way, and out came the Planck spectrum. And when he submitted this paper he asked Einstein to help him to publish it in Zeitschrift für Physik, Einstein immediately realized that this treatment of Bose, which was for light, for photons which have no rest mass, could be immediately applied to atoms and molecules. And so pretty much within no time, Einstein generalized Bose's treatment to atoms. And then for atoms, the treatment predicted Bose-Einstein condensation. For photons, you don't have Bose-Einstein condensation. But if you add a rest mass, the mass of an atom, and you have conservation of mass, then the black body spectrum turns into the Bose-Einstein distribution. And at sufficiently low temperature, the Bose-Einstein distribution has this phase transition into a Bose-Einstein condensate.
Okay. No, and I find very amazing that I think most people are familiar with Einstein's general theory of relativity or maybe his work in the beginnings of quantum mechanics, but it's really amazing how he really worked also in, I think he has a lot of apportation in statistical physics, for example, and it's really, it's too amazing actually the way like all the areas of physics that he contributed, like it's not really special relativities, quantum mechanics, like it's really in so many different areas in physics. It's very hard to, in a way it's hard to grasp how he can contribute so much to physics. It's too amazing maybe. Yeah.
He was a genius. He is really and it was an exceptional physicist. If you look at his work and what he covered, and yeah, he also did important major contributions to the development in quantum mechanics. Some people overemphasize that he was a skeptic with the Einstein-Rosen-Podolsky paradox, and people sometimes say Einstein said God is not rolling the dice, so he was never fully at ease with the statistical interpretation of quantum mechanics. But I think this is sometimes obscuring the fact that he really developed key ideas of quantum mechanics.
I mean, I think it's fair to say, I mean, he clearly understood quantum mechanics, but I guess his problems were more from maybe a philosophical or interpretational perspective. But I mean, he clearly knows quantum mechanics, because I think sometimes in the story people exaggerate a bit in terms that he had problems with this. But it's, I mean, he was one, I mean, he can be considered one of the founders of quantum mechanics.
Absolutely, yeah. Through the photoelectric effect, through the photon hypothesis, Bose-Einstein statistics, so he has made monumental contributions to quantum physics.
Okay, I see. And normally I did this to the end, but you kind of bring it up a bit, this subject about the problems with Einstein, about with quantum mechanics, and this so-called interpretation of quantum mechanics, and this whole debate of Einstein and Bohr, I think. And I always ask physicists about this so-called measurement problem, or about the interpretation of quantum mechanics, and what I find surprising so far is that I have found a very diverse range of answers in terms of some people don't think there's any type of problem. Some people find it's the most important problem. So I don't know if you have any particular opinion about this, or is it something, I don't know, about the so-called...
I'm probably more in the camp of people who would say I don't have any problem with it. Okay. Because quantum mechanics is a well-developed theory. For instance, QED is, tested to, I don't know, more than 10 decimal places. So quantum mechanics is one of the most precisely tested theories, and we have confirmed the predictions of quantum mechanics over and over and over again. So it's one of the most successful theories in physics. And I know when people feel uneasy about quantum mechanics, it is about what people call the quantum measurement process, but this is not related to the predictions of quantum mechanics and the usefulness of quantum mechanics. It's more an uneasiness about the philosophical interpretation of quantum mechanics. So I often feel when people say when people say there's a quantum measurement problem, I sometimes say, hey, wait a moment, this is not a problem of science, it's a problem of philosophy.
Okay.
Because for everything we do with quantum mechanics, we have a quantum mechanical system and we have a measurement apparatus, and we absolutely understand how to make those connections.
Okay.
Maybe I should say now, if you press me hard, I see a little problem when you ask me what is the wave function of the universe. Because if you talk about the wave function of the universe, there is nobody outside the universe to observe the wave function. Mm-hmm. And quantum measurements always need a quantum system and an outside observer. So if you press me hard, I would say, okay, maybe there is a scientific problem to understand also conceptually what is the wave function of the universe. But if you think about, every wave function of a microscopic system and we do measurements on them, we know exactly what we are doing.
Okay.
So I actually sometimes feel when people go around and say nobody understands quantum mechanics and quantum mechanics is mysterious, and I actually feel that this is even a little bit dangerous because it gives a message to the general public that we as scientists, we don't know what we are doing. And especially with quantum mechanics, we absolutely know what we are doing.
Yeah, but of course, no one can deny the experimental results of quantum mechanics. It has been an incredibly successful theory. So, I mean, it's clear that we can use quantum mechanics. We understand it. It has been experimentally verified. I mean, just the last Nobel Prize was one of the results that was verified. But still, I mean, I find a bit curious that even among the physics community, you can find a very diverse range of answers in terms of this issue, so to say it. But yeah, I mean, it's good to...
But people who debate, the different interpretations of quantum mechanics, for instance, the Bohr interpretation or the Copenhagen interpretation or the many worlds interpretation, I mean, if all these different interpretations do not make different predictions, this is a question which is untestable. And a scientific hypothesis should formulate alternatives, and we can do experiments to distinguish between alternative theories. But if we have alternative interpretations of quantum mechanics and there is no prediction which allows us to distinguish about it, then for me it's not a question of science. It's a question of personal preference, or you can say a question of philosophy.
And do you think it's always going to be untestable, or do you think there's the possibility that in the future there's going to be, I don't know, a time of test to the discerning between all these different interpretations, or do you see it as something impossible, so to say it, or highly unlikely? I don't understand. I don't know.
Well, it depends. I mean, if people postulate a different form of quantum mechanics and they make predictions, then it's testable. Okay. There is one school of thought which is related to Roger Penrose. He suggested that some collapse of the wave function is caused by gravity. And now some people have added nonlinear terms, new terms to the Schrödinger equation, and this is now making new predictions which can be tested. Okay. Unfortunately, some of those theories make predictions which would deviate from the predictions of quantum mechanics only when you have superposition states of macroscopic objects. And that this is something which is extremely hard to produce. However, there are few experimentalists who try to put a quantum object, macroscopic quantum object, into a superposition state to maybe verify or disprove some of those hypotheses that there is a gravitational form of decoherence involved in quantum mechanics. So what I just said is this is an example where people have come up with some predictions which are different from the normal predictions of quantum mechanics, and maybe with a big effort in the future, they can become testable.
Yeah. No, because I mean, I don't know if Einstein or Planck or these people ever thought, for example, about the possibility of building quantum computers, for example. And eventually, I mean, I know we have non-classical devices. I mean, there's still not the perfect quantum computer, but I mean, there has been incredibly a lot of progress in this area. And what I'm trying to
I would say definitely they didn't think of it. I think when quantum mechanics was developed, people always thought about, ensembles of atoms, ensembles of particles, and you do measurements. The idea to do measurements on single atoms and single photons, I think this was beyond what people envisioned when they developed quantum mechanics. There were even people, I think, who thought that you shouldn't apply the Schrödinger equation to single particles. They never thought about that. But then we eventually developed, the experimental tools, and we now understand theoretically, for instance, these beautiful experiments. If you have an ion in an ion trap and it does quantum jumps between, ground state and the metastable level, and you can really see how the wave function collapses in one state, then in the other one and such. So you really see quantum jumps. But even before those quantum jumps were discovered experimentally, some people thought this would be nonsense. This would not be how nature behaves. So I would say the step, also we use still the same quantum mechanical equations, but the way how to know what is the wave function applied to single microscopic objects. This is modern physics. This enables the quantum computer, and this was not on the mind of the people who developed quantum physics.
Okay, I see. I guess a bit my point is that I don't know, maybe in the future there are experiments that maybe doesn't seem likely now or not close, but I mean, if technology evolves, maybe there are certain experiments in quantum mechanics that could surprise us or that maybe could give us some more insights in terms of the foundation of quantum mechanics, or do you see this as something very unlikely?
Well, quantum mechanics has really been tested in a wide range of regimes. So it's not that our understanding of the world will be invalidated. It's a little bit like, Einstein's theory of relativity. It doesn't mean we cannot use Newton's equations. For 99% in your life, we can use Newton's equations and the engineers use them. It's just that Einstein taught us that when we go to extreme speeds, close to the speed of light, there are fundamental corrections. And maybe similar, just referring to the possibility that, when we combine quantum mechanics with gravity, that we find some gravitational form of decoherence. This could be important at the fundamental level, but it will only correct our understanding for systems in very extreme parameter ranges. Okay. As I said, maybe macroscopic superposition states, which are very, very difficult to create because they have very, very fast decoherence times. So, but yeah, that would, to discover that there is a new type of quantum mechanics needed to describe mesoscopic objects, this would be amazing. It would be an amazing discovery.
Okay. And we actually deviate a little, but I wanted to bring, of course, another amazing discovery or another amazing experiment, which of course was the Bose-Einstein Condensate. You talk about the theory, but maybe if you can talk a bit about the experiment. Something that caught my attention is, and I guess you could explain much better, of course, but one of the main techniques, I think it was laser cooling. And maybe one naively, initially when one think of lasers, maybe one naively could think about using lasers to heat stuff, not to cool. So maybe if you could explain the experiment a bit in general, in particular this point about laser cooling.
Yeah, so Bose-Einstein condensation was realized by, taking a gas of atoms down to very, very low temperature. And when I entered the field, some pioneers in atomic physics had just developed laser cooling. I joined the field in 1990, and people had developed amazing methods of laser cooling, and in 1997 they got the Nobel Prize for it. So laser cooling, which allowed to get into the microkelvin temperature regime, was the first step to reach Bose-Einstein condensation. We had to add a second cooling method to go from microkelvin to nanokelvin. But laser cooling was an absolutely important first step. Now, laser cooling itself is amazing, and it's actually, yes, it would defy the common understanding that lasers heat. But I always explain it like that. Lasers are a form of energy. And you have a black t-shirt on. If I would shine a powerful laser on your t-shirt, you would feel the heat because the photons disappear. The photon energy is converted into vibrations of the molecules in your t-shirt, and you would feel the heat. But in laser cooling, we use atoms which cannot absorb the photon. They can only absorb the photon for very, very short time, and then they have to re-emit the photon. So therefore, atoms are never absorbing the energy of the photon. They are not converting light into heat. So atoms, at least in some idealized form, do not absorb light. They scatter light, photon in and photon out. And then you would say, okay, if the photon is not absorbed, there is no cooling and no heating. But now we are looking at a smaller difference. The photon which is scattered can have a slightly higher or slightly lower frequency than the incident photon. The color of the light can change, and the simplest reason why this could happen is the Doppler effect. So if you arrange for a situation where the atoms scatter light, and the scattered photon has a little bit higher energy than the incident photon, then every time an atom scatters a photon, it radiates a little bit away of its energy. Okay. And then it gets colder and colder. Okay. And so this is what is behind all laser cooling schemes. You create a situation where the scattered light is slightly more energetic than the incoming light. Okay. And this enables atoms to literally radiate away their energy through the scattering of photons.
I see. Maybe, because maybe initially, if you could explain a bit how is this related? I mean, because I think in a Bose-Einstein condensate, you have to reach very low temperatures, right? So I guess in a way, maybe you could explain how did you apply this technique of laser cooling in terms of realizing the Bose-Einstein condensate, and maybe you could detail.
Yeah, I mean, we used laser cooling to the extent possible. We prepared laser-cooled samples of atoms, but those laser-cooled samples were still far away from Bose-Einstein condensation. And we also reached the limits of laser cooling, because if you try to apply laser cooling to colder and denser samples, the lasers actually start to heat. There are processes that the discreteness of the photon means that in normal laser cooling, there is a limiting temperature called the recoil temperature. You can only cool to that temperature, but you cannot get colder. When you get very dense atoms, and Bose-Einstein condensation is about cold and dense atoms, these dense atoms will absorb the light. There will be multiple scattering of light. The light is not just scattered once, it's scattered many, many times. And this causes limitations. So to make a long story short, laser cooling had reached a limit before Bose-Einstein condensation happened. So it was essential to devise a second method of cooling which could take the laser-cooled atoms to even lower temperatures. And this method was evaporative cooling. So the critical step to realize Bose-Einstein condensation is to find to combine both in a conceptual and a technical way two different cooling schemes: laser cooling and evaporative cooling.
Okay, I see. And yes, and from what I understand, at this period, because there was another group, I think, and they were the first, I think, the Bose-Einstein condensate, with it a bit after, I think. But still, I feel like in this period, when they were creating the first Bose-Einstein condensate, so to say, there was this competence, right? I think it was a group on Boulder, and I don't know, was it hard to deal with this kind of competence, or how do you look back on this period? I don't know.
Oh, it was an amazing scientific competition. There was this idea, which we shared at conferences, we talked about it, that we want to combine laser cooling with evaporative cooling. And there were two groups, one at Boulder and my group at MIT, who were working hard towards this goal. And for many years, there was a head-to-head race. We developed some method. The Boulder group learned from our methods and vice versa. So it was really good to have this competition. And then what happened is, it was actually almost fortunate that the two efforts, where we used different atoms and somewhat different methods, we reached the goal within 4 months. Okay. First, in June of 95, the group in Boulder, and then in September of 95, my group. And eventually it seemed that the community felt that this was a joint achievement, and then in the end, the Nobel Prize was shared between the group. But it was actually an amazing scientific competition, and I think it's good that science is competitive because it brings the best out of you.
Okay. Yeah, I think as long as it's a friendly competition where everybody can win, and I think it can give very good results. And I think this is a very good example of that. And yes, and looking back on that, I think because I was looking at some videos and sometimes people ask about applications. What can we do with Bose-Einstein Condensate? I mean, now it has passed some time, and has there been any type of maybe application in terms of this Bose-Einstein Condensate in terms of simulation, quantum simulation, or how do you look back about maybe your understanding or the possible, or how we handle this?
Depends if you talk about when you talk about applications. The whole field of cold atoms has led to applications, and it has, and maybe the big applications which have come out of it is in terms of better atomic clocks, and also in improvements in measuring accelerations. Accelerometers are important for navigation, are important for measuring the Earth acceleration, and there are commercial instruments which can now measure little g, the acceleration of the Earth, with very high precision using laser-cooled atoms. So these are two, it's not that, you find it in every household, but these are now precision scientific instruments for measuring time and acceleration, which are now used all over the world. And I would say this is a direct application of cold atoms. However, in most of the atomic clocks and atom interferometers, you don't need a Bose-Einstein condensate. You have a better signal-to-noise ratio if you use just a larger sample of laser-cooled atoms. Now, on a more scientific level, Bose-Einstein condensates or ultra-cold atoms in general are now used for quantum simulators, are used to learn something about many-body physics, learn about new materials. One could even say simulate materials using ultra-cold atoms as Lego pieces. So this is sort of, you can say application, but it's a very scientific application because it uses cold atoms as an instrument for further research.
Okay, no, but I think it's very amazing, and I think obviously with fundamental science, I mean, yes, sometimes it can lead to applications, not always, but still it's very amazing to explore the frontiers of our knowledge.
So quantum simulation is for me not yet a technological application as atom interferometry and atomic clocks. It's more a way to understand quantum mechanics more deeply, to understand new phenomena in materials. And so, yes, ultra-cold atoms have turned into an amazing research tool for that.
Okay, no, I really think it's amazing. And you just gave a talk, a very amazing talk, in which it seems like you're very invested in this subject of quantum simulation, in particular in using ultra-cold molecules. So I don't know if you gave a talk, but you just briefly explained about this area of your research that you're currently working.
Well, in today's talk, I talked about two directions in my research group. One is ultra-cold molecules, and the other one is experiments with the dysprosium atom, which is the most magnetic atom in the periodic table. In both cases, polar molecules which have an electric dipole moment, magnetic, atoms which have a very strong magnetic dipole moment. In both cases, it is about new kind of forces between the particles. Between polar molecules, we have strong electric forces. Between lanthanide atoms, we have strong magnetic forces. And the idea is now to understand new phenomena, create new materials where those magnetic or electric forces play an important role. Okay. And the important feature of those magnetic and electric forces are they are long-range forces. They act over longer distances than the forces we have used so far in ultra-cold atoms.
Okay, I see. And I think like one of the uses in research is to be able to simulate quantum systems, right? Maybe because there's this whole subject of quantum simulation, and I don't know.
Yeah, we have now for many years started to assemble quantum systems out of cold atoms and understand their behavior. And if we have new building blocks with long-range forces, there are other phenomena and other materials we can study.
Okay, I see. And something else that I want to ask, of course, with this experiment of the Bose-Einstein Condensate, you won the Nobel Prize. So I guess the question is, what it's like to win a Nobel Prize?
Well, to receive the Nobel Prize, of course, is an amazing acknowledgement. But I would always say that, the Nobel Prize is, it's important, it distinguishes science, but within the field, we know who has made discoveries, we know who has advanced the field, and some people get the Nobel Prize at the end of their career, but they were well respected and well known throughout their career. So I sometimes feel the Nobel Prize is more important for the perception of science from the outside than from the inside. From the inside, we know who has made the contribution. I can point to many people who have done, research at the level of a Nobel Prize, and it doesn't matter whether they get it or not. I know that they are great scientists. But if you give somebody a Nobel Prize, you become a representative for science, and the general public and politicians are listening to you because you are now distinguished as an outstanding scientist. So the Nobel Prize, I think we need it. It's good to have it because it helps to, highlight some directions in science, and it's good for science to have Nobel Prizes and to have some people who become spokespeople of the field. But I want to point out that the Nobel Prize is a little bit digital. Either you get it or you don't get it, whereas scientific accomplishments are often on a more, gradual scale that, you contribute to science in many steps and you're known for that. And the people who missed the Nobel Prize because they were maybe number 4 on the list and only 3 people could get it, they have done really amazing and great science and are famous for that as well.
Okay. No, but there's this positive aspect that, of course, I don't know, with the Bose-Einstein Condensate, for example, I guess, like it kind of towards the attention to this topic, maybe general audience that maybe will not be interested in this, suddenly they are more curious to know what is this about. So I guess it kind of, I guess, increases the interest from the general public.
But there is a difference. The Nobel Prize was given in Bose-Einstein condensation 6 years after the discovery. So that's when the field was still developing. And of course, the Nobel Committee put a highlight on a field where there was a lot of research activities. This is really different from a Nobel Prize, which is given 40 years after the discovery of something, when, this effect is already in the textbook of physics, and maybe it's no longer, such an active field. Okay. So I think there are sometimes it's actually good if Nobel Prizes are timely, but we know how Nobel Prizes are awarded. It sometimes takes maybe a long time because before the Nobel Committee is convinced that this was really such an important discovery.
Okay, so, and because honestly, the truth is normally the Nobel Prize people earn it at if they earn it at a very old age, but you earned it quite young. I think you were like 43 or 44 when you won the Nobel Prize, I think. Which for a Nobel Prize is something very young. And I guess the question is, because I don't know, but because you mentioned that when people who won the Nobel Prize, suddenly they kind of become like a spokesperson for science, and their opinion matters in terms of politics and stuff like that. And was this a big pressure for you, or did you enjoy it, or I don't know, how did you deal with this part that suddenly?
I was rather young when I got the Nobel Prize, and my life was exciting and full I had small children with family, and I loved to do research, so I didn't want to change my life. So I was careful, and I would say I only allowed Nobel activities, to talk to politicians, to take invited lectures or all that. I tried to make sure that this was only taking 10% of my time. Okay. So I wanted to continue my life, and I've actually done it.
Okay, that's amazing. Yes, maybe this is a bit of a random question, but it's something that sometimes I ask the guest. Is there a writer or a philosopher or a thinker outside of science that you admire, or is there someone that you think you like the way this person thinks? I don't know, someone outside of science that you consider as very interesting opinions, or has maybe a favorite author or something?
When I was a student, I was interested in philosophy of science, how philosophers explain the accomplishment of science and how science is changing our worldview. And of course, the philosopher to describe science were Kant, Popper, and Thomas Kuhn. So I like to read about them. So I was really inspired by them.
Okay, I see. And I was reading some opinion by some philosopher of science that obviously science is advancing, and we're still there. I mean, clearly there's a lot of experiments going on, and there has been a lot of improvements. But I was reading one article when it described it in terms of fundamental science. For example, if you compare the beginning of the 20th century, which is when quantum mechanics started, general relativity, special relativity, we have all these really fundamental, really breakthroughs in fundamental science. And it seems when you look at the current age or the current times, I have the impression that at least in terms of fundamental science, the foundations of physics, there has not been a breakthrough of that magnitude like it was quantum mechanics or general relativity. Do you think there is a philosophical or maybe an institutional reason because of this? Because I mean, right now we have much more physicists working, we have internet, we have so much more tools. So why do you think that is? Oh, first, if you agree, maybe you don't agree, of course, or
I don't know. Fields have become more mature, and of course, Newtonian physics, quantum mechanics, and theory of relativity are amazing milestones, and you cannot expect those to happen again and again and again, because you would say, special relativity was understanding what happens at high speeds, quantum mechanics is what happens in the microscopic world, general relativity is what happens in, the universe. So this covers a lot, and there is not any length scale or any speed scale left where we do not have developed a theory. Okay. So in this bigger picture thing, you could say that maybe the macroscopic world, cosmology, we have now developed at least pretty good theories and pretty good descriptions for everything. On the other hand, I don't feel there are still so many fundamental discoveries. Just think about neutrino physics, a question about neutrino mass. Think about gravitational waves, which have just recently been detected. Think about the discoveries, experimental discoveries of dark energy and dark matter. I mean, this is amazing and fundamental. So I don't know. I would sometimes say, hey, physics in the 21st century is as exciting and as fundamental as physics in the 20th century. It just happens in a different direction and a different scale.
Okay, that's good. No, I think I agree. There's obviously great discoveries. There's still great science done, and yes, I will not take much more of your time. But honestly, thank you very much. It was very great to speak with you. So yeah, thank you very much, and thank you, Brexit.
You're welcome.
Thanks. Thank you very much.
Okay.